Hey everyone, welcome to your Unit 6B video. This is the second lesson in this unit. We're still talking about circular motion in this unit, all things curves, circles, orbits, all of that good stuff. Today we're going to get to talk about loop-de-loops, so we're going to get a little bit into roller coasters, which is kind of fun. All right, so the first thing we need to chat about is these types of problems. So yesterday we had a few problems where we were talking actually about horizontal circles, like maybe you saw that word in some of the problems. So picture someone swinging a lasso around, right? That would be kind of a horizontal circle like that. But what happens if we turn this into a vertical circle? Kind of think back to that water example, right? We were, for the most part, swinging that in a vertical circle. If your circular motion is just horizontal, you can just focus on the centripetal force exerted by an object. But if your motion is vertical, gravity is going to have to be considered, because now I'm thinking net force. I'll have centripetal force pulling something to the center of the circular path. So here's my vertical circular path over here. At the top, I'm going to have centripetal force. Maybe, I don't know, that could be tension of a string. That could be something else. That's going to be pulling this object towards the center, but you do have to consider its weight. So remember, weight is mass times gravity. Weight is a type of force. Down at the bottom of this, your centripetal force is still keeping you towards the center, right? It's still pointing towards the center of your circular path. Weight is always acting downwards. So your centripetal force could potentially change, or maybe your velocity is changing. That's kind of the stuff that we're going to be talking about today. So we're going to be talking about roller coasters. We're going to be talking about, Ferris wheels, stuff like that. Anything that has a vertical circle. We'll have some problems where we have like a vertical washer on a string kind of problem. So the washer on a string problem, that's a little more generic for us, just to get comfortable with what we're talking about. But we do get into roller coasters. All right, so here's our first example. I have a 0.15 kilogram ball, so I know mass, 0.15 kilograms. It's on the end of a 1.10 meter long cord, and it's swung in a vertical circle. So that's our R value there. Picture someone holding the end of this cord and then swinging it around in a vertical circle, something like that. Okay, so that's your R value, is 1.10 meters. Determine the minimum speed. So V is what we're going to try to find. The ball must have at the top of its arc, so all the way up here, so that the ball continues moving in a circle, and calculate the tension in the cord at the at the bottom of the arc. And at that point, we're going to assume the speed is 2 times that which it was at the top. Okay, so first, think about this problem intuitively. If I'm swinging something around in a vertical circle, and if you're in 220, go into one of the cabinets and find that washer on a string that I had out yesterday. If you swing it too slowly, it's not going to make it through the full circle. If you swing it fast enough, then it will actually, keep moving at the top of the arc. So here they're asking us, what's that minimum velocity needed to ensure that this thing keeps traveling in a circular path? To do that, we're going to actually start with our centripetal force equation. And I'm using this, sum, this sigma, because for these vertical problems, you do have a sum of forces. So in this case, what are the different forces acting on this thing? Well, I'm going to have some kind of tension, and I'm going to call this FT1 because later on they're going to ask us to calculate tension in the bottom when I'm at the bottom of the arc. So I'm going to actually maybe have different tensions in this problem. So I'm going to label it FT1. And then you're also going to have, let me just erase the cord over here. You're also going to have weight, or just mass times gravity, okay? So when I'm at the top of my arc, both of these are pointing towards the center of the circle. I am going to choose towards the center. I'm going to make a little note down here. Choose towards the center as positive. You do not have to do this. This is just something that we are going to assign. And remember that G, if you ever see G, we're just going to use positive 10 meters per second squared. Okay, so what I'm saying is Anytime I have a force that's pointing towards the center of my circle, I'm going to say it's positive. If it's pointing away from the center of my circle, I'm going to say it's negative, okay? That is the convention that I am choosing. I'm going to be consistent with it throughout the whole problem. You could officially, for problems like this, choose a different convention, and that would be okay and that would work. This is how I am going to choose to explain this problem to you, okay? This is how your textbook does it for this type of problem as well. Okay, so back to our equation. I'm using my centripetal force. The sum of my forces then, both of these are pointing towards the center of my circle, so they're both positive. Ft1 plus mg equals mv squared over r. I know mass, I know g, I know r. We're trying to solve for v. Let's take a second and figure out what would Ft1 be. So again, we want to kind of pause and think of this intuitively. Your minimum speed, which is what we're trying to find, so minimum velocity or speed, will occur when your tension is just about slack. So just right about at that point where this tension is going to go to zero. At that point, gravity, the force due to gravity, will be the only force acting. And because it's acting towards the center of the circle, it does still count as a centripetal force, okay? The cord will kind of go limp. All right. So if we know that, then if I'm trying to find minimum speed, I can say, okay, that's right at that point where tension is going to go to zero. And we are left with just mg equals mv squared over r. I do know my mass for this problem, but we can see that I can actually go ahead and cancel it out because I have an m on both sides of my equal sign. So I'm left with g equals v squared over r. Let's rearrange that to get v by itself. V squared equals g times r. Take the square root. Your minimum speed is going to occur at the square root of g times r. Go ahead and plug in your numbers. G is 10 meters per second squared. R is 1.1 meters. When you go ahead and plug that in, you're going to get something about 3.32 meters per second. So this again would be our minimum velocity to maintain our circular path. Okay, that's the first part of the problem. If you need to pause, go back, rewatch, ask a friend, say, what the heck is Miss Curlin talking about? Do what you got to do. Make this make sense to you, all right? I'm using my centripetal force equation. In this case, I have multiple forces acting, so I had to use this sum. Our two forces are tension of the string and weight. They're both pointing towards the center of the circle, so I said they're both positive. That's the convention I'm using. Our minimum speed occurs when that tension starts to just reach zero, that cord just starts going limp, and gravity is the only thing keeping us in that circular path. So you set Ft1 equal to 0, and you solve your equation out. Okay, second part of the problem. Now they're looking at the bottom. If you think about the forces acting, well, tension is still pointing towards the center of my circle. I'm going to call it Ft2 because Ft2 could be different than Ft1. Your weight is going to be acting always downwards. Okay, so if we follow that same convention, the sum of my centripetal forces equals mv squared over r. Well, now I'm going to have positive Ft2, but minus mass times gravity minus that weight because it's pointing away from the center of my circle. And that's going to be equal to mv squared over r. Our v for problem, they told us to just assume that the speed is 2 times that at the top. So v2 over here, we'll call it 2 because we're dealing with like the second case, would be 2 v1. So we're going to get 6.64 meters per second. So all I did was take that. Okay, the little second is not going to draw in. There we go. All I did was take our velocity that we just found, multiplied it by 2. Okay. So at this point, you know mg, v, r. We're trying to solve for Ft2. Rearrange your equation a little bit to add mg to the other side. So you have mv2 squared over r plus mg. Go ahead and plug in everything that you know. You know your mass. You know v2 is 6.64 meters per second squared. Your radius, we said, was 1.1 meters plus your mass, 0.15 kilograms, times g, 10 meters per second squared. Okay, squared. There we go. plug all of that into your calculator, you're going to end up with FT2 equals 7.5 newtons. And double check your units, right? Make sure your units work out. Over here, I'm going to get kilograms times meters over second squared. Over here, you would get same thing, kilograms times meters over second squared. So those are both what a Newton is. So your units do work out. All right, so that's your first example. There's a lot going on in this first example. We did not start light today. We just kind of dove right in. Some of it is new, right? So I used a new convention here. We're using a new formula. A lot of the ideas are still the same, right? Really, if you go to the heart of what we're doing, I'm still doing F equals ma. That's still what I'm doing, but now with circular motion, A changes a little bit, F changes a little bit. Okay, the next example is just kind of a think it through. A rider on a Ferris wheel moves in a vertical circle of radius r at constant speed v. So they're not giving us any numbers. It's more theoretical right now, more conceptual. Is the normal force that the seat exerts on the rider at the top of the wheel less than, more than, or the same as the force exerted by the seat at the bottom of the wheel? So you have your vertical circle here. You have your rider going around. They're asking us to consider the top and the very bottom. You're sitting on a seat. Your weight is always pointing down. How do you think your normal force would change here? So take a second, reason this out, pause the video, do what you gotta do. So our answer for this one would be less than. So weight is part of the sum of centripetal forces in a helpful way at the top. So what I mean by that is at the top, your weight is pointing towards the center. Okay, so your weight is going to help keep you in this circular path, and your normal force would be kind of pointing upwards, actually, right? So that would be pointing upwards over here. At the bottom, normal force would be pointing up, and your weight would be still kind of pointing down. So it kind of swaps a little bit. At the top, gravity is kind of keeping you in your circle. At the bottom, your normal force is kind of keeping you in the circle. So at the top, your normal force would be less than the force exerted by the seat at the bottom of the wheel. All right, example 3. This one is a little bit different. So the Ferris wheel, you're sitting on a seat the whole time. You're not flipping upside down. Hopefully you're not flipping upside down on a Ferris wheel. But what if you have like a loop-de-loop on a roller coaster? So you have a roller coaster that goes around like this and then keeps going. What if we're looking at this case right up here where you are hanging upside down? At what minimum speed must a roller coaster be traveling when upside down at the top of a circle so that passengers will not fall out? This is pretty crucial stuff. So I don't know if any of you want to be engineers. I've talked to a few of you about this. I know we're looking at a few different fields. You could go into roller coaster engineering. Like, that's a field of study, which in a different life, that would be what I would do. Either that or concert design. This is a whole thing that people need to think about. There's tons of different safety precautions that must be considered for roller coasters. So this is a real world problem in a weird way. The only thing we know here is that the radius of curvature is 7.4 meters. Here's my little diagram. And yes, I'm going to ask you to draw diagrams. Diagrams are not meant to hurt you. They are always meant to help you. Just draw the diagram. Okay, so think about this. If you're upside down, well, you have a normal force acting on you, right? Your butt is against a seat, and it's not sinking through the seat, so there is some kind of normal force, but now the seat is kind of pushing you down, so consider your normal force as acting towards the center of your curve, and you have weight acting on you, okay? Mass times gravity. Both of those are pointing towards the center. I would consider both those to be positive in this case. Once again, positive for our convention means pointing towards the center of the circle. Okay, so I'm going to use my centripetal force equation. I have normal force. I have weight. That equals mv squared over r. I'm trying to figure out what's that minimum speed so that I'm not going to just be falling out. So the moment that we want to consider is right when Fn starts to equal 0. Once Fn equals 0, that means butts are not on, oh, yikes, let me try that again. That means butts are not on seats which is not great. So passengers at this point, the more proper way to say it is passengers aren't in contact with the car, which is not great. It can be fun for a moment, and then hopefully you have some kind of belt or bar keeping you from just completely falling out. They're kind of in free fall at this time, okay? Once again, hopefully you have a bar kind of holding you in. So there might be some other forces at play, but we want to consider that instant right when normal force goes to zero, when you're kind of falling away from the seat right before a bar or something else has caught you. Okay, that's the moment we're considering. So I'm going to say that this Fn term is going to drop to zero, and I'm going to be left with a pretty similar equation as example 1. This is cool. I don't care about the mass. I do not care about the mass of the person, right? It drops out. I didn't know mass. I don't need to know mass. I'm going to get the same kind of thing we got before. So you're going to have gr equals v squared. Take the square root of both sides. V is going to equal the square root of gr. Gravity is always going to stay the same, right? Gravity is always 10 meters per second squared. Your r is the thing that's going to change. So your radius is really the thing that's going to determine the minimum speed for safety. Okay, so our r in this case was 7.4 meters. Plug this all into your calculator. Your minimum speed is going to be about 8.6 meters per second. Okay, so the larger your radius, the larger your minimum speed is going to have to be to ensure that you actually do make it all the way around the loop. The smaller your radius, the smaller your minimum speed would be to ensure that you make it around the loop. All right, I'm going to pause there. You have part B of this video. Yes, there's a lot of stuff. I'm asking that you continue learning while I am gone. I know you all can do it. Catch you in the next video.